Okay, so this was that one when I told you guys to look at the practice for the rolling things with the energies. Okay, so this is one of the examples I wanted to do today. So we're going to do number 5. I am going to draw a picture. If they don't give you a picture, it's always a good idea to draw one. All right, and it's going to roll down this ramp, and the ramp has a length of 3 meters. All right, so what ways can we solve for the velocity at the bottom? Conservation of energy is the one I would use. Okay, so conservation of energy. Is there another way we could do it? Yeah, forces and kinematics. You're going to get the same expression as you do with conservation of energy. Conservation of energy, way easier, okay? All right, so in order to do conservation of energy, what energy am I starting with at the top? Gravitational. And what must that equal at the bottom? Kinetic. But is this object going to be rolling? Yeah, so we're going to have translational and rotational at the bottom. All right, so what is the equation for gravitational potential energy? mgh. And translational kinetic energy? 1/2 mv squared. And rotational kinetic energy? And the rotational inertia or moment of inertia, yep. Angular velocity squared. Okay, so there's our expression. So how can I get the height of my ramp over here? If I know the length and I know the angle is 35. Yep, so the length sine of 35 is going to get me the height. I think it was 1.7 or 1.17. All right, 1.72 to be exact. Oh my goodness. Okay, so now we have an expression though with linear quantities and we have an expression with angular quantities. So what do we want to do? We want to have all one or the other. Since they're asking for a linear speed, it's easier to calculate the linear speed and then convert that to an angular for these. So rotational inertia for a solid cylinder. What is that equal to? 1/2 mr squared. Do you have to memorize that for the AP test? No. Okay. They're either going to give it to you or you would be solving for it and they would give you the other information. Okay. You do not have to memorize those. All right. How do I get an angular velocity into a linear velocity? So linear velocity is equal to angular velocity times what? Radius. Okay, so that means angular velocity is the linear velocity divided by the radius. All right, so now I'm going to take this expression for the angular velocity and plug it in there. This expression for the rotational inertia, and I'm going to plug it in there. So now we have mgh equals 1/2 mv squared plus 1/2 times 1/2 mr squared times the velocity over the radius squared. So that means I square everything inside my parentheses, so I get velocity squared over radius squared. All right. At this point, you could plug in a bunch of numbers if you wanted to, but a lot of the AP test stuff is not going to have numbers. So let's reduce this all down. Do I have the same mass in every single term? Yes. So what happens to that? Yep, it reduces. All right, what else can I reduce? We're almost there. What should I do before that?
The r squared.
I can reduce the r squareds, okay? Now something's going to happen with the 2. So let me rewrite this first. So I'm going to have the gravitational field strength times the height is equal to the mass times the velocity, 1/2 the mass times velocity squared, plus 1/2 times 1/2, what's that going to get me? Oops, yes it is. Sorry. It's a bad habit. All right, 1/2 the velocity squared. Plus, what's 1/2 times 1/2? 1/4 velocity squared. So, had you multiplied through by 2, you would still have to account for a 1/2 over there. Okay, so that's an easy math error to make. So be really careful. All right, how do I add these two together now? What do I have to do? Lowest common denominator, right? So this becomes 2/4. Or like Izzy said, it's GH equals 3/4 V squared. All right, then getting velocity by itself, multiply both sides by the reciprocal. That's equal to V squared. Take the square root. There's your velocity at the end. For the linear, that's the one they give in the answer key. And then to get the angular, you're just going to take that linear velocity and divide it by the radius, which is not in the answer key, but I think you all can figure that out. Questions there? It would be different if it was a solid sphere, right? Because that's 2/5 mr squared for rotational inertia. And it would be different if it was a ring. So they're all going to have a different velocity at the bottom. All right? But the method to get there is exactly the same. The only thing that would be different is the rotational inertia equation that you would substitute in up here. Okay? All right. The other one we looked at was the yo-yo question. Oops. I hate when it does that. All right. Must be on the next one. Yo-yo. Right here, number 7. Okay, so we talked about torque problems with torque diagrams, okay? For beams, ladders, rods, torque diagrams are going to be a straight line, all right? For things that are round like this, your torque diagram is going to be like the object. It's going to be round, okay? So this is a yo-yo. So yo-yos have an inner cylinder and then the outer radius, okay? So tension, remember, always pulls in the direction exactly like it looks in the picture. So that tension is around the centerpiece. So that's my tension force there. And then what other force is acting on the yo-yo? The gravitational force. And the gravitational force acts at the center of mass. Okay, so then we have our inner radius here, which is R0. And then we have this big outer radius here, which is just R. Okay, just going from the picture. All right, so previously when we had objects that were not rotating, we would look at the linear, or Newton's second law for linear motion. So is this accelerating or not accelerating? Yeah, they told us we're looking for the acceleration, so it's safe to assume it is accelerating. So we have a Newton's second law problem. And then the other side of that equation comes from our diagram. So motion is in the downward direction for the yo-yo. That's what we're interested in. The yo-yo is moving down. So that's the direction I should choose for positive. So that means that my gravitational force down here, which is actually equal to the mass times the gravitational field strength, is the positive force. And you have to subtract the tension from that one. Otherwise, you would have had to make sure you had a negative over here in the acceleration if you do tension minus the gravitational force. Okay, so be careful with that with your signs.
How do you know it's going down?
Because have you ever done a yo-yo?
Yeah, but like it goes up, right?
But once you let it go, it's going to go down. And they're also telling you the rotation here. So if it's rotating that way, it has to be going down. If it was going up, it would be rotating the other way. Okay. They're not usually going to do them going up. And they're not usually going to do yo-yos. Okay. So this one's a little more like a next level of difficulty from what you guys will actually see. Okay. Okay, so there's my second law equation. But do we have an equation for tension? No, we don't have an equation for tension, right? If we don't know the acceleration, so right now I have two unknowns. I have acceleration and tension. So I have one equation with two unknowns. So I need another equation for one of them to substitute back in there to solve for the other one. Okay, that's a lot of what Physics C is. So anything that's capable of rotating or is rotating has a torque acting on it to cause or maintain that rotation. Okay? So I'm going to have the sum of my torques, or my net torque, which is rotational inertia or moment of inertia times the acceleration, angular acceleration. But there's also always a force causing that torque. So which of the two is causing the rotation? The gravitational force or the tension? The tension, because if the tension was gone, it wouldn't rotate anymore. It would just fall straight down. Okay, we're okay with that? So my tension times the radius, R naught, because that's the part of the, that's where the string is. Okay, so that's the radius you have to use. All right, then I can combine these two together. So my tension times that radius equals the rotational inertia times the angular acceleration. So now I can divide both sides by that radius. And now I have an equation with known quantities that I can substitute in for the tension force. Okay. So I'm going to take this piece now and sub it in up here. So now I have an equation that says the mass times the acceleration is equal to the gravitational force minus the rotational inertia. Oops, we forgot a step. Because I'm still going to have an angular acceleration in there. We have to get our angular, we either have to make our angular acceleration in terms of linear acceleration, or we have to change our linear acceleration over here into angular. Okay? But they're asking you for linear, so we need to convert our angular to linear. So linear acceleration is equal to the angular acceleration times the radius. So that means my angular acceleration must equal my linear acceleration, divided by the radius. It's not going to let me write it. It's too close to the arrow. All right, now I need to take that piece and put it in here. So what I end up in here then is the linear acceleration over that radius squared. All right, that means now that I'm over here, it's going to be my rotational inertia times the linear acceleration divided by that radius squared. Okay, because that's my expression now here, and I'm going to put that in up here for tension. Then it becomes an algebra problem. Combining like terms by adding this term to both sides equals the gravitational force. You can factor out the linear rotation from the left side, and then divide both sides by that expression. So your linear acceleration is the weight or the gravitational force on the yo-yo divided by its mass plus its rotational inertia divided by that radius squared. And now it just becomes a plug in your given information. Okay? The answers are on the back of here. I also put the answer key on Canvas, so all of these worked out is on Canvas. Okay, so if you haven't looked at these yet, I highly suggest looking at these before next time. Next time you have a free response quiz. All right, the rest of the part of this problem are just kinematic problems, because now that we know acceleration, you can figure out the time by taking your linear acceleration now. It starts from rest, and y is the length of the string, because that's how far it'll fall. And then what's its linear speed at the bottom? That's just another kinematic equation. Again, that's 0. And once you have that velocity, you can do the translational kinetic energy and all of that good stuff. Okay, yes, no, maybe? Okay, I want to talk then, we're going to do the ladder, we're going to look at the ladder problem today. All right, I'm going to take you through one of those. The rotation problems on the multiple choice test are, there's not that many. Somewhere between 4 and 5, sometimes as little as 3 in the multiple choice. There will be a free response question that is rotation. Okay, it's guaranteed. One of the 3 free response will be a rotation problem. So either similar to what we just did, where you're using torque and net force and figuring out an acceleration, then using kinematics to figure out time or a displacement, or using something to get a final velocity and a kinetic energy, something like that. Okay, they're going to embed that. There will be a rotation problem. It could also be like the torque problem we did in the quiz the other day. And we're due for one of those pretty soon. A torque problem. They did one in 2008. They did one in 2014. I'm not sure if they did one last year or not. I haven't looked at last year's questions yet. But we'll be looking at those when we do our full test review. Okay? All right, let's look at the ladder problem then. When do we use torque? This didn't come up in here because we had done an example problem at the beginning of the class. But I had a lot of people at home that just did a force problem for the torque. Okay, so when do we use torque? Anytime we have an object that is capable of rotating. So for example, if I had a bar and I was had 2 tensions holding it up, and I were to take away one of those tensions, would that rotate if I took away a tension? Yes, it's going to rotate in that direction. So this is a torque problem. Okay, it's probably a torque and a linear force problem, but it's definitely a torque problem. Okay. The other example I could show you that is not going to be a torque problem is if I had a box on a table. If the table breaks, does the box rotate? No, it's just going to fall straight down. Okay. Same with if I had a box hanging by a tension here. If I suddenly got rid of the tension, it's just going to fall straight down. It's not going to rotate. Okay. So if it's something that is capable of rotating, then you have to use torque. So let's look at the ladder problem. So this one was from the practice problems you guys had, not last time, but the time before. So last week, Thursday, I gave you this question right here. All right, but you can do it on notebook paper. That's fine. Okay, so is this ladder that the bear is on capable of rotating? So that is, if we were to eliminate this wall over here, would the ladder rotate? It would, because once it hit the ground, it would be flat like that. So it has to rotate in order to become flat. Okay? The same thing happens if we were to eliminate the friction over here. Then, again, it's going to slide out. It's going to rotate because it's going to end up flat. So it has to rotate to become flat. Okay? So let's talk about all the forces we have acting on the ladder. So what's one of them? The gravitational force on the bear or on the ladder?
We're talking about the ladder on the ladder.
Okay, on the ladder. Where will the gravitational force on the ladder act? At the center, because it's uniform. Assume it's uniform unless they tell you something different. All right, what's another force acting on the ladder? The bear. And the gravitational force is going to act on his center of mass, and it's going to go straight down. Oh, sorry. We're not doing the force diagram for the bear, we're doing it for the ladder. So on the ladder, it's going to be right there. All right, another force acting on the ladder. There's 3 more.
Normal force
Which normal force?
from the ground.
From the ground. Okay. So I'm going to call it the normal force from the floor just because the G gets kind of confused with the gravitational force, okay? All right, what's another one?
Normal force from the wall.
Force from the wall. What direction is that one going to be in? Perpendicular, so it's a normal force from the wall. All right, there's one more. Got to have something balancing out that normal force. What's it going to be? Yeah, the friction. So the friction must go in that direction because I have to have balanced forces in both the vertical and the horizontal direction. Okay? If the ladder slips, it's going to slip in that direction, so friction has to go in the opposite direction. All right, so this is a ladder. It's going to require a torque diagram. So my torque diagram is going to look exactly like the ladder did in the picture. That way we don't mess up any angles. Okay? All right, so here's my torque diagram. So we're going to take all of the forces we just identified and put them on our torque diagram at their proper locations. So the normal force from the wall, the frictional force from the floor, the normal force from the floor, the gravitational force from the ladder, which is 400 newtons, and the gravitational force from the bear, which was, bless you, equal to 2,000 newtons. Okay. I'm also going to go ahead and put my lengths on here. So before I do that, we have to decide where our 0 or our rotation point is going to be. So where is our 0 position? Where should we put it? At the bottom. That's exactly where I would put it too, because right now we have 1, 2, 3 unknown forces. So I would put it where we have 2 unknowns. Okay? Now, technically, can I figure out my normal force from this diagram, the normal force from the floor? Yeah, then I could put the pivot at the top, figure out my frictional force, and go from there. I would put it at the bottom, and I would start there. So that's my 0 position. So then this makes this the 8 meter mark. Oh, let me put it under because we're going to be writing something there in a minute. That's my 8 meter mark. This is 6.3 meters, and the center of mass of the ladder is at 4 meters. Okay, we have a 50-degree angle right here. Where else on this diagram do we know for sure there's a 50-degree angle? At the top, between the normal force and the ladder. So let me move this out of my way. I'm going to put the 6.3 down here. All right. So then the normal force from the wall, well, that is not perpendicular to the ladder. Remember, in order to calculate torque, we need the perpendicular piece. So the perpendicular piece of that normal force is there. And then it also has a horizontal piece going that way. Well, if 50 degrees is down here, where is the 50 degrees then in the components? So these are perpendicular. So that means this one's 40, which puts the 50 up here. So my normal force from the wall, that vertical component, is the normal force times the sine of the angle. Are we okay with that? Okay. hold on just for a second. I'm going to save this video, and then I'm going to screenshot this so that we don't have to start over. I'm going to save this